Hi, this is Kaiyuan Liu from Indiana University. Today I would like to share with my work about how to predict complete tandem spectrum from peptide sequences. This work is also published on SAS Analytical Chemistry. Mass spectra and peptides are closely connected. When we obtain some spectrum like this, we can refer to approaches like database search or de novo sequencing to infer its original peptides. This pathway has been widely studied. However, the reverse pathway from peptides to its corresponding spectrum have only a few existing studies, and they all have serious limitations. The current prevailing approaches to predict spectra are based on the idea of backbone ions. Here we refer backbone ions as a complete set of ABC XYZ ions and their neutral loss derivatives. Although backbone ions make the majority part of the spectrum, however, the predictions are far from complete. Like this spectrum, which remarked all backbone ions on the bottom, shows that there are noticeable portion of peaks are not from backbone ions. Actually, like this pair plot shows, there are nearly 30% of intensities are not from backbone ions. So the question is, can we predict complete tandem mass spectra? However, the problem is that the fragmentation mechanisms for non-backbone ions remains unknown. So how can we solve this? We are inspired by the impressive success of deep learning models in domains like image recognitions and neural language processing. Thus, we propose that with some carefully designed network, we can also let our model learn fragmentation mechanisms from massive data by itself, even those mechanisms are unknown to our humans. Before introducing our method, I would like to briefly summarize the data format and the evaluation standards first. We chose to represent a spectrum by a sparse vector. Like for this example spectrum, we cut this spectrum into small bins of 0.1 and over z, and this will give us a vector of 20,000 dimensions. For evaluation, it's natural to evaluate the performance by computing the cosine similarity between corresponding vectors. Okay, let's talk about the model now. We name our model as platform, and this is the overall workflow for it. We need to feed the one-hot encoded peptide and other necessary information to the network, like the target charge state and so on. The model will take the input and predict the 20,000 dimension vector as output. Please refer to our publication on analytical chemistry for more details of the model. You can see that we don't provide any fragmentation rules in advance, and we do not distinguish between backbone ions and other peaks. We first focus on predicting spectra of unmodified charge 2 and charge 3 HCD peptides. We collected 4 human cell spectral datasets. Generally, we use around 2.5 million spectra for the training process, and we hold out around 40,000 spectra for testing purpose. Of course, the testing set has no overlap with the training set. We compare our model with the backbone-only predictors. First, we compare with 3 previous published models, which all based on the idea of backbone ions. We also present a implementation version of PDIP, which predicts all types of backbone ions for comparing. Finally, we also compared with the theoretical perfect backbone predictions, which is made by extracting backbone ions from real spectra. This approach will give us an estimation of upper bound performance of all backbone ion-based models. Here, we can see that when comparing with a complete spectrum, even a theoretical perfect backbone predictions can only achieve an average cosine similarity of 0.74 and 0.7, far from our prediction performance of 0.82 and 0.78. Those performances are not far from the average similarity between experimental replicants, and it's not surprisingly much better than the performance of previous backbone-only methods. Here, I would like to show you some examples of our predictions. The upper half is a real spectrum with backbone ions labeled in orange, and the lower half is our prediction. It's clear that our model not only predicts backbone ions, but also covers most non-backbone ions. Till now, we are talking about the charge 2 and charge 3 spectra only. However, what if we want to predict spectra of other charges or even ETD spectra? How about modified peptides and non-trivial peptides? Those predictions are feasible, however, facing the same challenge that we have insufficient training data for it, which means we will have poor performance. So, our solution is multitask learning. Multitask learning is a variation of transfer learning. Its idea is that fermentation knowledges learned from common spectra can also be applied to predict spectra of uncommon types. Here is our modified model. To address the problem of insufficient samples, this joint model can train on spectra of all mixed charges and types. However, we cannot directly mix trained data together because the network will be confused. Thus, we added many auxiliary branches that predict the precursor mass, charge state, and the fermentation type. Those auxiliary tasks will stabilize the training process and will prevent overfitting. Thus, our model will be able to share knowledge between different types of predictions. With the help of multitask learning, we can use less than 10% of training data, but also achieve a comparably good enough performance on both charge 1 and charge 4 ISCB spectra. You can see that the performance is also much better than direct training method, which is just mixing all types of training data together. Also, by multitask learning approaches, using less than 10% of the total number of HCD spectra, we can achieve high enough performance on ETD spectra for charge 2, charge 3, and charge 4. It's much better than the performance of direct training. Due to the time limit, I will pass the performance on modified peptides and non-trivial peptides. In conclusion, the purpose of this work is to predict complete tandem mass spectra, rather than just predict backbone ions and their derivatives. To solve this problem, we use a convolutional network to learn fermentation patterns and rules automatically from large datasets. We also address the problem of insufficient training data by multitask learning. As a result, we built the first complete spectral prediction model, which also performs much better than all previous backbone ion-based methods. Finally, we'd like to thank Dr. Nuno for helpful discussions. Thank you.